All right, jumping into the pre-recorded lecture for chapter 3, we're going to be covering stoichiometry. Looking at the definition of stoichiometry, it's defined as the study of quantities of materials consumed and produced in chemical reactions. So in order to better understand stoichiometry, you first have to understand the concept of relative atomic mass. So to do so, we're going to explore this idea of counting by weight. So you would count by weight in these listed scenarios: when objects behave as though they're all identical, when atoms are too small to count, or if you need the average mass of the object. So an example that could be listed from one of these is if you're trying to count how many grains of sand there are on the beach. Because they're so small and they're all almost identical, you would try and first figure out how much it weighs, like it's just a handful of sand or a bag full of sand, and then you would find out how much an individual sand grain weighs, and then you would find the average amongst them all. All right, so here's an example of us trying to apply this method. So we have a pile of marbles that weighs about 394 grams. You know that 10 marbles weigh 37.6 grams. How many marbles are in the pile? So to start, what I would do is try to figure out how much one marble weighs. And doing so, I would set it up by dividing this 10 marbles by 37.6. Because it's such an easy equation, all you have to do is move the decimal place over 1. So now we know that each marble weighs 3.76 grams. And now all we have to do is just divide that by the weight that's already existed in the pile. So you have 394.8 grams divided by the 3.76 grams per marble, right? So remember that that's here. So in doing so, you would just run this calculation. You understand that you are dividing by another division symbol, which is going to place this on top. So now marbles will be up there, grams cancels out, and we have an answer of 105 marbles. All right, so that is counting by weight. I apologize for this writing tool. It is extremely difficult to use. But anyway, moving on to the next slide. All right, so there is the worked out equation of how you would set this problem up. You can go through that as you need. Next. All right, so looking at atomic masses. So the example that they gave us is an atomic mass of 12 and an element of C, which is carbon. So that's the standard atomic mass, which is represented on the periodic table, and it has 12 mass units. So realistically, it's not always at 12 for its atomic mass. It exists in different isotopes, as we've uncovered in the previous chapters. And here is a breakdown of how frequently carbon exists in each isotope. So 98.89% of the time it exists around 12. It has an atomic mass of 12. And then on the other hands right here, you'll see that it's about 1.11% in some other type of isotope. So because of this, we can actually calculate the average percent between these different numbers. So let's move to the next slide. All right, so it has the 98.89% of the 12 unit mass, and then you have the 1.11 at 13.0034. So essentially what they did, if you were writing out a formula for this, you would just do the percentage, multiply it by the first isotope, right? Isotope 1, and then you're adding it to the percentage of isotope X, right? Because this could continue to go on. There could be 3, 4, 5 different isotopes, and you would just keep doing the same thing. So this could be isotope 2, you do it again, isotope 3. And that's essentially where it's taking you. So doing that calculation, you would get the answer that is 12.01. So that is the average atomic mass for carbon, and that's why it's also listed out on the periodic table. So it exists. This is the average between all of the isotopes, and that's what's listed on the periodic table. All right. Looking at this, it says that the average atomic mass for carbon says even though the natural carbon does not contain a single atom with a mass of 12.01, for stoichiometric purposes, which is just making sure that we have whole numbers and everything works out perfectly, we can consider carbon to be composed of only one type of atom, which is a mass of 12.01. It really helps with our numbers, and you'll see that in a little bit. So this enables us to count atoms of natural carbon by weighing a sample of carbon. So what does that mean? Let's look forward. So what they actually do is they run a sample through this thing called a mass spectrometer. They take your sample. In the previous case, we were working with, what was the name of it? Carbon. So they put a small sample of carbon. They bombard it right here. It goes through this process where they heat it up and it ionizes the carbon. And the carbon would run through this little machine right here. And then these magnets, it's gonna slit through these little slits right here and then run towards this magnetic field. The magnet, now that they're ionized, meaning that they're charged, it's going to push them in a certain direction. So the heavier ions are going to not get pushed as far because they're larger, and that's what puts them into this spot on the mass spectrometer. Then once it gets hit, it records the number of hits, the number of ions that hits each region, and that tells you how much of each isotope is present. So here's a little image displaying that. But for our previous example, carbon mostly exists as carbon-12, so that recorded the most ion hits. There's a cool video right here if you want to watch that too. Moving on. So we have an example problem. It says an element consists of 62.6% of an isotope with a mass of 186.956 units. And here's another percentage of an isotope with a mass of 184. So we would calculate the average atomic mass by doing that exact formula that I was listing out earlier, right? Which is the percentage, and then you do the various element, and then it's just the random element, and then you add it together. So in setting that up, here is the way that the equation breaks down. I thought I put it up right here. Let's see. I thought I wrote it down on the slide, but I guess not. So essentially, after you plug in those numbers into the formula, you're going to get 186.2. And then using that average atomic mass, you can look it up on the periodic table, and you will find that it is rhenium. All right, moving on. So now we're going to explore the concept of the mole. Such a fun concept. Okay, so it says the number equal to the number of carbon atoms in exactly 12 grams of pure carbon-12, right? So that's essentially saying that the molar mass, the average atomic mass, which is 12.01 grams of carbon, is equivalent to 1 mole of carbon. That's really what that sentence was saying. So 1 mole consists of 6.022 times 10 to the 23rd atoms. That is according to Avogadro's number. So they actually listed out the mole conversions right here. 1 mole is equal to 6.022 times 10 to the 23rd atoms, and it's also equal to 12.01 grams. So this is how you're going to be able to convert in and out. You're going to go from grams to moles, and then moles to atoms, and then atoms to moles, and so forth. So that's kind of going to help you through these next few problems. All right, here's some practice. It says to calculate the number of iron atoms in a 4.48 mole sample of iron. So we're going to just work with what we are given. So we're given moles, so we start in moles. Because we're in moles and we know that there's a direct conversion from moles to atoms, we don't need to go to grams. This is our start place, and we can get directly to our end place. So just starting with our 4.48 grams, you're going to multiply that by Avogadro's number, which is a 6.022 times 10 to the 23rd, and that will be your result. Okay? So it actually ends up equating to 2.70 times 10 to the 24th iron atoms. Okay, so again, excuse my cursor tool right here. It's a little bit limiting. But just a general rule of thumb that I wrote down when you're trying to go through these stoichiometry problems is just when in doubt, convert to moles. Moles is like it's something that you can always fall back on because you know that moles can convert to grams easily, and then moles also converts to atoms. Okay, so if you're just not sure where you are, you can always go back a step and go right into moles. All right. Using molar mass. Okay, so in the previous examples, we were only assuming that there was one element present. So we would use the molar mass of the single element, and that would be the average atomic mass. But now, if we're going to be working with compounds, compounds are going to have a total mass that consists of the molar mass of all of the elements that are within it. So in this example right here of water, we have H2, which means that you would have to always multiply by the subscript. So there's 2 hydrogens, and hydrogen has a mass of 1.008. So then the mass of hydrogen present in this compound is going to actually be 2.016. And then the same thing goes for oxygen. Oxygen's average atomic mass is 16. You would add these together to get a total mass for this compound, a total molar mass for the compound, and it's 18.02 grams per mole. Some additional practice right here, they use barium nitrate. Again, you have to make sure that you're adding all of these subscripts to these other parts of the compound. So barium stands alone, it doesn't have the subscript right here. But then once you get to this nitrate, this 2 actually distributes to everything within the parentheses. So you're going to have 2 atoms of nitrogen, and then you have 6 atoms of oxygen. So it's important to make sure that you're always accounting for the subscripts that are present, because that will change the difference of the total molar mass. All right, so then adding these up, you get 261.35 for the molar mass. Okay, moving on, we have another concept check for molar mass. It says, which of the following is the closest to the average mass of 1 atom of copper? So go ahead and pause and try and figure this out. All right, so now that you guys have taken that time, hopefully what you'll realize right here is the highlighted part of the question. It says that 1 atom. So 1 atom is different from your typical just grams that you would be working with. Atoms are going to be existing in some type of scientific notation as because of the 6.022 formula that was brought in by Avogadro. So right away, I would think that this is E because we're working with a really, really small number in this case. All right. Moving to the next slide. There's a follow-up concept check. So it says to calculate the number of copper atoms in 63.55 grams of a sample of copper. So the first thing that you would do, you have to figure out where you are. So starting with atoms, that's our first step work. We're trying to figure out how many atoms are present. What we are given is 63.55 grams of copper. So in order to get to our final results, we got to go from grams to moles and then to atoms, right? Because there's not really a shortcut to jump straight from grams to atoms. So like I was saying previously, when in doubt, convert to moles. So you're going to go from grams to moles, and then that moles is going to get you to atoms. So let's see. What does it equate to? It equates to 6.022 times 10 to the 23rd grams, or copper atoms. Okay. I would write all of it out, but this cursor is just it's just incredibly difficult. So I'm just going to assume that you wrote down the 63.55 grams, put the time sign in a line, and then you put the molar mass down here of the copper, and then you put 1 mole up on top, and then you went from moles. I ended up writing it out. But 1 mole of copper is equal to 6.022, and so forth. So you kind of get the idea of those. All right, moving to the next concept check. It says, which of the following 100-gram samples contains the greatest number of atoms? So the first thing that I'm seeing right here is that all of them have the same amount. There's 100 grams of each. So it wants to know how many atoms essentially each one has. But because we have the same amount to start, we actually get to save a step. So all I would do for each one of these is I would convert from grams and get them into moles. And whichever of these produces the highest total moles is going to also produce the highest number of atoms, right? If you have more moles, that means you have a higher positive number and you're multiplying by another positive number, which is going to be a greater positive number. So it would be a lot to write out right there, but I think I went ahead and put it in this slide. I didn't put it in there. But essentially, you would just convert all of these into moles. So you'd have 100 grams of each of them. So you'd have 100 grams of magnesium. You put it down here, time sign in a line. You have your molar mass of magnesium that you find directly from your periodic table. It's 24.305 times on the top. You're trying to convert to moles of magnesium, and then you get an answer, right? The idea is that magnesium has the smallest molar mass, therefore it's going to become the highest positive number, right? Because if you're dividing by a bigger number, you're going to have a smaller result. So if you were comparing it to, let's say, zinc has a molar mass of 65.38, which means that it's going to produce a smaller number. And then the same thing goes for silver that has a molar mass of 103. All right, rank the following according to the number of atoms from greatest to least. So the difference in this question from the previous question is that now each one has their own individual amount. So you're starting with a different quantity, which means that you would have to start from that individual ratio, and you'd have to go through the order. So you'd go from grams, and then you're converting that to moles, and then you're going to have to go into atoms in order to see what the following are. So I believe that did I put this one on there? So this is the order of them right here. After you were to convert each of these from grams to moles, you'll see that zinc actually converts to 1.07 moles, and then you have silver converts to 1 mole, and then you have your magnesium going to 864 moles. So I actually did those separately. But again, just like the last problem, your zinc is going to have the highest number of atoms because it's the largest whole number, right? So it's 1.07, and then silver would come next, followed by magnesium. Okay. Consider separate 100-gram samples of each of the following. So here are 4 different compounds that are listed. It says rank them from greatest to least number of oxygen atoms. So in order to do that, what you're going to do is you're essentially going to divide by the number of moles that are present within this. So you're going to start, all of these are going to start with your 100 grams, and then you're going to convert to moles based off the compound that you're given. So 100 grams and H2O, you're going to use the molar mass for H2O, which is 18.02. So that's the grams there. You're going to go 1 mole of H2O on top. Now that you are in moles, then you'll be able to determine the number of atoms, right? So you'll do another time sign in a line. 1 mole of H2O, you can't see it anymore, is equivalent to 6.02. Okay, so after you do these calculations, go ahead and take a second to calculate all of the atoms for each of these respective compounds, and then you'll see that this is the way that they rank. I calculated them and posted them here because I figured I wasn't going to be able to write them all, but you should be getting these values for all of these compounds. And then that's when you'll be able to rank them. So these should all say atoms. All right, moving on. Okay, so what we've been using over the course of this process is essentially what we talked about previously with systematic learning processes, is just constantly checking in with yourself, asking where you are, where are we going, how do we get there, and like defining like a specific process. So going through stoichiometry, you have to use that. It's really important to know where you're starting. So it says to read the problem, decide what the goal is. How do you get there, to work backwards from the final goal and decide where to start? And then you have to make sure it makes sense. Like, are you converting from grams to atoms? Like, you have to check to make sure that it's a real conversion process, or just that you're dotting your I's and crossing your T's. Okay, so one thing to take with you all the time. Now we are jumping into percent composition of compounds. So in essence, when you're trying to do mass percent, you're trying to find out how much of a specific element is in a compound. So if I'm throwing out a random example with H2O and I want to find out the mass percent of oxygen, I would be putting in the total molar mass of oxygen in this compound and dividing by the total mass of the compound. Okay, so you would set that up and multiply by 100 to find the percentage. They actually illustrated an example for us right here. This I think came from the book. So it says iron 3 oxide. You would we just went through the process of converting names to formulas. So you find out that it's Fe2O3. So we're trying to figure out how much iron is present. So iron, there are 2 iron atoms, so we got to make sure we put that on the outside, and then you put the average atomic mass of iron in here. That gets you a total of 111.7. You divide that by the total molar mass for the compound. You multiply by 100, and then that gets you 69.94%. That's how much iron is. Iron makes up 69.94% of this entire compound. Okay. Moving on. It says to consider separate 100-gram samples of each of the following. So it gave us the same 4 compounds that we were working with earlier, except now it wants us to rank them from the highest to lowest percent oxygen by mass. So we're going to have to isolate oxygen in each of these 4 cases, and you're just trying to find the percent oxygen of each one. So in order to do that, you're going to just set it up. So this last time I did this first one, so I'll do this next one now. So looking at this, you only have 1 oxygen atom present, so you have 16 grams, and then you would calculate the total molar mass that is present right here. So I know that nitrogen has a mass of 14.007. I'd multiply that by 2. That gets me 28.014, and then I'd add that to my 16. Okay, and then you'd multiply that by 100, and then that calculates to, give me a second. All right, you get 36 point, oh, did I do this backwards? Let me see. Pull it back. Sorry, I lost my calculation. All right, hopping back in. I lost my calculation previously, but we'll go right back to where we were. So Now that I got this calculation right here, I got, let's see, it was 36.35%. So that is the percentage of oxygen that is within this compound right here. So you do the same for all of these following right here, and you would find that the order goes first, second, third, and fourth right here. All right. So you got some good practice. These are the calculations that you should have gotten for each of the respective compounds. All right. Determining the formula of a compound. So you have your formula. You have two different types of formulas. There's an empirical formula and then there's a molecular formula. Your empirical formula is the simplest whole number ratio. So you need to make sure that it's in a whole number. We don't want to have like a C 2.5 present. That just wouldn't work out very well for our number. So making sure that it's a whole number. All right, let me get this pen again. So, and then your molecular formula is going to be the empirical formula within parentheses times however extra many atoms are actually present. Because molecular formula could just be just a much larger total molar mass. So you have to understand that these two also follow the law of definite proportions. So if I'm starting off with CH3, and this is my empirical formula, but then I find out that I have a much larger total molar mass, and I find out that my actual molecular formula turns out to be C3, then that means that my H would also have to be, it'd be C3H9, or you would represent it as CH3, and then you put it in the parentheses like this. Because whatever happens to one also has to happen to the other by rule of the law of definite proportions. Okay, so let's get some practice in with these right here. It says the composition of apidic acid is 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen by mass. The molar mass of the compound is 146 grams per mole. What is the empirical formula? And then what is the molecular formula? So this one actually is there's quite a few steps to do in this problem. I want you to try and do this on your own. So take a minute to pause and try and approach this and break it down into parts. And then we're going to work on this in Monday's lecture if you haven't watched it, if we haven't already had class before you're watching this video. But in essence, what you're going to be doing is you're going to assume 100 grams of this entire compound is present. That means that all of these are going to just become, you're going to drop the percentage and you'll have 49.3% or 49.3 grams carbon and 6.9 hydrogen and so forth. And then you're going to divide by their individual molar mass. So you would divide this by 12.01, you divide this by 1.01, and so forth to calculate the number of moles. So you need to first find moles. That would be the first step. And then now that you have moles, you would use the smallest number of moles that was produced, and you're going to divide all three of these by the smallest number. So you're going to have the carbon divided by whatever the least common moles was. And you're going to do that for all of them, which is going to produce a ratio. So it should produce a ratio like carbon, I think, is going to be equal to 2.5, and then your hydrogen is going to be equal to, I think it's 1.5, and so forth. But then moving forward, you can't have decimals, so then you would just double all of these because you don't want decimals present in your empirical formula. So you would just try to find the next common whole number that exists among these, and then that's what would get you your empirical formula. So the results of this end up becoming C3H5O2. So if you got that on your individual practice, that's great. And then using this 146, you are going to just figure out what this total molar mass is relative to this one and how much you would need to multiply in order to get this total molar mass to equal that one. and then I think it's just doubling it. Okay, so practice it on your own. If it doesn't make sense, we're going to come back to this in class. All right, yeah, and I also wrote the answers on there. Okay. So you would get C6H10O4. All right, determining the formula of a compound. So here we have a representation of a chemical reaction. We have the reactants on the left side. That will always be the case, reactants on the left, and then you have your products on the right. So products is what you end with. The reactants are what you start. These are your initial. So the reactants, that's exactly what I just said. Yeah, so you have the reactants on the left, the products on the right. This is going to be the basis for all of your chemical reactions. Okay, let's look at the next slide. So the equation has to be balanced as per the law of conservation of mass. We have to make sure that we have the same number, like the same number of atoms present on this side that we have on this side. So if you were to go through and add these all up into parts, you have 2 carbons here, you have 2 carbons there, you have 6 hydrogens here, 6 hydrogens, and so forth. So you need to make sure that they're balanced because what happens to one side has to happen to the other. Okay, so in this case, you have established certain mole ratios. So for every 3 atoms of oxygen, that 3 moles of oxygen that were produced, you have 1 mole of this ethanol that was produced. And then and so forth. So you can compare the ratio of moles produced and reacted to each other. Okay, so that'll be really helpful once we get into limiting reagent problems. So it's kind of building off what we were just talking about. The balanced equation represents an overall ratio of the reactants and products. It's not always what actually happens in a reaction. That would be in a perfect reaction, everything reacts completely and fully, but that's just not the way that everything works in nature, and that's where limiting reactants come into play. So just as a base rule, we're going to use the coefficients in a balanced equation to decide the amount of each reactant that is used and the amount of each product that is formed. So this will make sense in just a second. I would ask that you guys write down these general rules for writing and balancing chemical equations. So as always, the first step, you want to determine what reaction is occurring, what are the reactants, what are the products. A lot of times this might be involved reading a word problem. And when you see something where it says like 2 different types of compounds react, you know that they're going to be on the reactants. It could also say burns, and that lets you know you're in a combustion reaction. So the oxygen is always going to be on the reactants, and then you're going to have carbon dioxide and water produced in the product. So it's being able to determine what's present, and then you'll write and balance the equation to summarize that first step. So you want to make sure that it's balanced, and then once it's balanced, then you can move on, and then you can start working with your numbers that are present. So here is some practice. Go ahead and take a second on this one on your own. Okay, so looking at this question, it's asking which of the following are correct. If you were to have done this, you'll see that there are multiple answers. So you have that, you have 3 and 4. So the reason being, we don't ideally want to put decimals present, but this is not untrue. So these are all following the law of definite proportions. What happened from this equation right here, they doubled it, and now all of these they've been doubled. See, you see the 2, the 5, the 2, the 1. And then in this one, it was quadrupled, or from this reaction, it was doubled. So they're all following the same proportion. You have to make sure that you have the same amount on both sides as well. So they're following a lot of the laws that we studied in the last chapter. All right, next concept check. Which of the following are true concerning balanced equations? All right, so go ahead and take a look at that for a second. Try it on your own. Okay, coming back, looking at these answers, you'll see that the main overarching rule is that atoms are neither created nor destroyed. So it's not necessarily the number of molecules, but it's the atoms that are present within these reactions. Moving on to the next slide. So here is some extra information with regards to balancing chemical reactions. It says the number of atoms of each type of element must be the same on both sides, always. And then the subscripts can't be changed. That is really important. You also must account for all of the subscripts. The next point is that a balanced equation tells us the ratio of number of molecules which reacts and are produced in a chemical reaction. So we're going to get into that, I think, in the next couple of slides. And then finally, coefficients can be fractions. However, they're usually given as the lowest integer of multiples. So you always do want to represent it as a whole number. For the sake of our class, it's just cleaner and easier to put them as a whole number. So if it involves doubling something or tripling, however it is to get to a whole number, go ahead and do so. Looking at stoichiometric calculations. So for these calculations, chemical equations can be used to relate the masses of reacting chemicals. Here are some additional rules for these stoichiometric calculations. So when you're calculating, you want to make sure it's balanced. That's the first step. Converting the known mass or product to moles. So it's balancing, converting to moles. Then you're setting up an equation to establish mole ratios. Then once you have a common mole ratio, you're going to go from that ratio to moles and then back to grams. So this is kind of a general process, and it's outlined here on the next slide. I like the way that this is laid out for you. So you have your balanced chemical equation. You're going to find the ratios that exist, right? The coefficients that are in front. And then it's going to ask you to convert. It's going to say you have an initial mass of something on your reactants. How much of this mass was produced in the products? So you're going to start with your initial mass. You're going to always convert to moles. You're going to use the mole ratio of your initial mass or from the initial compound. And then that ratio is going to compare to the one that was in the product that you're trying to get to. Now that you're in moles there, you convert from moles to grams, and then you get to your final answer. So it's a little bit abstract, but this is actually, once you get it down, this is a really helpful image. It really breaks down the steps. So here's an example of what it is referring to. So in this reaction right here, you have phosphorus and oxygen go in to produce, what would that be? Diphosphorus pentaoxide. So you're starting with the 6.25 grams of phosphorus that's burned, right? So I was saying earlier, burned indicates that it's going to be a combustion reaction, or it's going to have oxygen present on the reactants, okay? So it says, what mass of oxygen does it combine with? So the first step in this process is going to be starting with your initial thing that they gave you, which was the grams of phosphorus. So you have 6.25 your grams of phosphorus. And what did the thing say the next step was? You want to convert to moles. So you have your grams of phosphorus, which in this case is actually P4. You want to keep these always consistent. So you have grams of P4. So if you were to calculate what that is, it's 123.88 per 1 mole of P4. Now that you have your 1 mole of P4, the next step that you would do is compare the mole ratios. So you were trying to go from moles of phosphorus, and you want to get that to moles of oxygen, right? So you're going to set up what you have given. You were given 1 mole of phosphorus. So the ratio is 1 mole of phosphorus relative to 5 moles of your air or oxygen, O2. And then you would continue this process moving down here. Now that you have moles of oxygen, you have to determine what is the grams of oxygen. So 1 mole because you're trying to get rid of your units, is going to be equivalent to the 32, where'd it go? 32 grams of oxygen. And I apologize for the writing of this. I hope you guys kind of see what the process is. Essentially, you start with your number and you're dividing by it, so you're removing it. So you're out of grams now, and at this point you're in moles. So from moles, now you need to get to moles of how much that you had initially. So moles, and this is the conversion to get you back into the moles of oxygen, and so forth. Okay, so I think I actually wrote it out for you on here. Let's see. There it is. That's much cleaner than what I was working with right here. There you go. So here, if you can follow that, that is the setup for this process. And then at the end, once you get to your final product, which is in grams, you're going to get 8.07 grams of oxygen. All right. Exercise part 2. So it says that methane reacts with oxygen in the air to produce carbon dioxide and water. And then you have another example. It wants you to write the balanced equations for each of these reactions. So go ahead and set them up. Put the correct things on the reactants and your products on the right-hand side. So when it says it reacts with oxygen, you know that that's going to be on the left, and then produces. So everything right here that it produces will be in your products. So practice that, and then continue the video when you're ready. So you'll see that this is the final outcome that was produced. Everything here is balanced, making sure that you have the same number of atoms on both sides. And then in your second example, you should have this as well. Okay. Moving on. So now we are it's asking us with regards to the exact same questions that we just found the chemical reactions for, and we've balanced out the reactions. It says, what mass of ammonia would produce the same amount of water as 1 gram of methane reacting with excess oxygen? Okay, so what I want you to do is, again, take some time to think about this problem systematically and think about what you need to start with, what is it asking you, and where you need to go. So I don't actually expect you to do this one. We'll come to this problem on Monday in class, and then we'll talk about that together. But if you can list out the different things, like where you need to go and all the steps behind it, then that would be as much as I would want you to cover so far. So go ahead and take a moment to try and do that on your own. All right. Now that you've taken that time, here is a little bit of a rundown. So it was saying, where are we going? The goal of this was to find the mass of ammonia that would produce the same amount of water as 1 gram of methane reacting with excess oxygen. So what we need to know to answer this question is how much water is produced from 1 gram of methane and excess oxygen. And then we would also need to know how much ammonia is needed to produce the amount of water calculated. So it's really about just breaking down these problems. And I will say that sometimes when you get like higher level AP questions, they really try to throw all of these different types of processes to confuse you. But if you're able to break this up into parts, which is what we're going to practice doing, it's really going to help you move forward and answer test questions, because most of it is just understanding what they're asking you. And then the rest of it is just it becomes pretty elementary after that. Okay, so moving to the next topic, we have the concept of limiting reactants. So limiting reactants are reactants that run out first. So they're on the left-hand side, and they're going to run out first and limit the amount of product that can be formed. So previously, we were talking about the stoichiometric reactions, where those go to completion and it's like a perfect world and everything reacts and there's nothing left over. But in the real world, most things aren't going to run to completion. So your limiting reactant is going to be the atom or compound that runs out first, and the other one is still going to have leftover product. So we're going to figure out how you do these calculations a little bit here, and then we're going to explore this idea more in Monday's lecture to kind of help you all to conceptualize it. So to determine which reactant is limiting, calculate correct amounts of products that will be formed. So let's see. So it gave you a couple of images to help you conceptualize this. So like I was mentioning, in a stoichiometric mixture, you have everything going to completion, right? So you have your N2, you have your hydrogens, and then it reacts and then goes into these perfect NH3 compounds, and everything's the same, right? The law of conservation of mass, what's happening here is perfectly happening here. Perfect ideal world. But then you have a limiting reactant mixture where in this case, we actually have less H2 in our initial reaction. We don't have the amount of H2 necessary for it to bind with all of the nitrogen that we have present. We would need an additional 6 hydrogens to bind with these remaining atoms right here. So the way that the reaction produces is some of it reacted to completion, but then we also have an excess of nitrogen present. So here is the breakdown of it. The limiting reactant in the previous reaction was the hydrogen. It ran out before we were able to digest or consume all of the hydrogen or the nitrogen that was present. So here is a concept check. It says, which of the following reaction mixtures would produce the greatest amount of product? Each involves a reaction symbolized by this equation right here. Okay, so keep in mind that these ratios still have to stay true. So go ahead and try and answer this question right here. All right, so now that we have answered this question, hopefully you guys got this answer down at the bottom, that each would produce the same amount of product. And the reason being, in order to produce more in the final reaction, we're going to need both a 2-to-1 ratio. It's going to have to double. So if we want any more than 2 atoms of this hydrogen compound, then we're going to need both of these to double. So that means that we would have to produce 4 H2s and then 2 oxygen atoms right here, which would allow us to get to 4. But anything less, like we could have 4 hydrogens present, but then we only have 1 of the oxygen, these extra hydrogens are just going to be left as excess. They're not going to allow us to form 4 total or an extra couple of hydrogen atoms. So you have to make sure that you have everything before you can produce more. And all of these would be too limiting, right? So you have 3 moles of hydrogen, but you only have 1 mole of oxygen. So you wouldn't be able to form an additional compound. And the same goes for all of these other ones. All right. So it says that what you'll notice from the previous example is that we can't just add the total moles of all the reactants and decide which reactant mixtures make the most product. We have to always consider the ratio that's existing in the balanced equation. All right, next concept check. It says you know that chemical A reacts with chemical B. You react 10 grams of A with 10 grams of B. What information do you need to know in order to determine the mass of product that will be produced? All right, so go ahead and take a second to think about this systematically. All right, so hopefully what you realized in the previous example is that in order to actually move forward with this example, you need to know the molar mass of A and B, and you also need to know the molar mass of, the molar mass of the product too. None of that was given. And then you also would need to know the mole ratios that exist between the different types of atoms or compounds that were in this reaction. So those are going to be essential, and in this next slide, we're going to be given them. So given the same initial amounts of A and B, it says what mass of product will be produced given that the molar mass of A is 10 grams per mole, B is 20 grams per mole, and C is 25 grams per mole. They react according to the equation listed. So go ahead and try and approach this as best you can, and then go ahead and replay it, and then I'll start talking about it. Okay, so looking at the example given, we see that the initial ratio is that we would have to have 1 mole of A for every 3 moles of B. And then that would allow us to produce 2 moles of C. However, in this example right here, when you convert from grams to moles, so you have the 10, you divide that by 10, you're going to get 1 mole of A. So we have our 1 mole of A present just like we do in our example problem. So we're good there. That would be enough to move forward with this reaction. However, we have 10 grams of B, and you would divide that by 20 grams, because that's how much we were given in this initial reaction. That is going to be 0.5 moles of B, where typically, so we're going to have 0.5 moles of B right here, and we would typically need 3 moles of B for this to actually become 2 of C, right? You would need 1 mole of A and 3 of B to produce 2 of these C's. And in this case, we only have half a mole. So in order to account for that, what we're going to do is we're actually going to have to divide this 0.5 by 3, because that's going to be the percentage that we actually have. We don't have all 3 of these B's. We have 0.5 out of 3, which is a percentage of B. So doing that process right there, you have, this is the way that it breaks down. And now you would multiply that, because this has to be the same as, this is the mole ratio relative to the mole ratio on this side. So then you're going to multiply that by your 2, right? Because we're supposed to produce 2. So in this case, now we're going to have a new product though. Instead of it being 2, it's going to be 2 times whatever this new percentage was. And in doing so, we're going to get an answer. So the answer is 0.5 divided by 3 times 2. It becomes about 1/3. So we produced about 1/3 the amount of C. We have only 1/3 of C now. This is in moles. And now we were given the molar mass. So you would just multiply by the molar mass. So you have the moles of C right there. You'd put your time sign in a line, moles on the bottom, and then your grams on top. So what is 1.1/3 times 25? You're going to see that that is equal to 8.33. And that is how many grams of C-react based off of what we were given to start with. Okay. So I hope that makes sense. I apologize that I can't write all of this out. But that is how you do this one. So it highlighted, it actually goes through and highlights all of the factors that you're looking at. So you had your A, then you had your B, and then it lets you know that this is your C. So it's kind of trying to guide you through the systematic process. All right. Moving into the last concept is the percent yield. So with percent yield, it's an indicator for the efficiency of a laboratory or industrial reaction. So we're trying to figure out, okay, how much of it did we actually produce, right? We're talking about this limiting and the excess, but how much of it did we actually get as opposed to how much was supposed to be produced? So we have the actual yield is what we get, our recorded results, and theoretical is going to be, in a perfect world, if something went to completion, that's going to be the number that's listed here. You multiply that by 100, and then that gets you your percent yield. All right, so in this reaction right here, it says, what is the mass of P4, or what mass of P4 is needed to produce 85 grams of PF3 if the reaction has a 69.4% yield? So we're trying to get to P4. This is our end right here. So we're going to need to work backwards to get to P4. But what we are given is we're giving everything in reverse. So we know that we have 64.9. So that is our percent yield. So we got to set up our percent yield equation. Well, what was our actual? Well, our actual that we need to produce 85 grams, right? We need to produce 85 grams. And then the theoretical is what we don't know. So we would basically just solve for x in this example right here. And then in doing so, that would allow us to determine the grams of PF3 that was needed initially. So this is going to equal 130.97 grams of PF3. All right, so now that we have grams of PF3, we're going to use this mole ratio to figure out what mass of P we would need to actually produce this amount right here. So you would set it up, you would convert to moles, and then after you convert to moles, you would do the mole ratio. Now that you're in your mole ratio, you would go back to moles of the P4, and then you would go convert to grams of P4 using the molar mass. I apologize that I don't have, like, I can't write all of that out because of the way that this view is. But what I did do is I went ahead and wrote out the first part of the calculation. The next one you can go ahead and do, and I could run over it in class too if need be. Okay, so the final answer you would get is 46.1 grams of P4. All right, and that is it. Thank you. And if you have any questions, please bring them to lecture with you, and we'll go ahead and try and tackle that together. All right, thank you.